Let's solve this problem. Okay, find free variation response, which means that from this problem we can start by divide 2 by 2. So we have this one, x dot plus 6x dot plus 34x equal to 0. Okay, especially for this one, okay, for free variation, excitation is 0. From this point, we can solve this one separately. Actually, you can choose one of these two. If I start the first one, okay, by equating this one from x dot plus 2 zeta omega sub n x dot plus omega sub n square x equal to 0. Okay, the point from this one is that I can equating omega sub n, okay, equal to square root of 34 for the natural frequency. Okay, and the second term, okay, we have 2 zeta omega sub n equal to 6. Or in this case, okay, we can have this one omega sub n equal to 3. And if I solve this one, this becomes 3 divided by omega sub n, which is square root of 34. Okay, at this condition, we can see that 3 a lot less than square root of 34, which means that it is less than 1. Or in this case, this is the indication that this system is under damped system. Okay, that's gonna be the point from this one. And when we know that it is under damped, the free vibration response is in the form of E minus zeta omega sub nt A cosine omega sub nt plus B sine omega t. I write it wrong here. This got to be omega sub t at the natural frequency. As I told you, another way for this one, okay, instead of determining the damping ratio to see that it is under damped, we can find this one by the characteristic equation, okay, which transform the equation to become r squared plus 6r plus 34 equal to 0. And then we can find the root. There are two roots, r sub 1, r sub 2, minus 6 plus minus square root of 36 minus 4, 16, 136 divided by 2. You can see that this becomes minus 3 plus minus, inside the square root, you see that this becomes square root of minus 100. So this becomes j square root of 100 is 10. Divide by 2. So we just do that. Divide by 2 becomes 5. Okay, which you can observe that this is going to be the condition for complex root. There are two roots, so condition of complex roots also indicate that the system is under damped. So we have two ways to determine to see that when it's gonna be what type of system: over damped, critically damped, under damped, and no damped. This is gonna be the condition that we have. Before I continue solving this one thing that you can see that the solution here, Okay, there is theta omega sub n with these three. I already have this one for you. Okay, omega sub d. I can do this one to you to show to you. This point here, omega sub d equal to omega sub n 1 minus theta square. Omega sub n is square root of 34 square root of 1 minus theta square. Okay, with this one here become 9 divided by 34, or in this case you get 34 minus 9 divided by square root of 34. Okay, it cancels with the one in the front of the square root. Okay, and this come out to be square root of 25, or it is 5. So then if I substitute into this function, so it become e to the minus 3t a cosine plus b sine omega sub d. We have it equal to 5. Okay, these are 5. Okay, if I would like to indicate, I may say this is going to be 3, 4, let's say this 4, 5. Comparing with the root, when we find the root, we can see that the roots before that, we would like to maybe use this space here. R sub 1, R sub 2 equal to minus theta omega sub n. Go back when we learn on the underdam, the root of the characteristic of underdam can be written by this one, plus minus j omega sub d. So you can mention this term. Okay, that's gonna be 3. Okay, we get this one instead, and that's the real part. Okay, the real part is going to be the exponential part. Okay, and then omega sub d. Okay, this is going to be this imaginary part, or imaginary number for this one, and that's going to be omega sub d. Okay, but if you're not so sure, you can recalculate. Okay, by using this theta and omega sub n. Okay, that's gonna be for, I might say this 5, 6, okay, maybe 7, okay, let's say 8 and 9. Okay, from 9, we know initial condition given by this one, at time equal to 0, gonna be f of 0 equal to e to the 0, a cosine 0, plus b sine 0. Okay, this is 0, so we're gonna have just only af. Okay, sine of 0. I should put letter 0. You might confuse 0 symbol in computer programming. You might put O for this one. So that's gonna be the 0 time. Okay, so we get the first one. Okay, a equal to 0. Okay, I can do this differently by combine this one. Okay, we can see that x of t. Okay, since a equal to 0. Okay, this will be to e to the minus 3t. A is 0. Okay, so we get this one become b sine 5t. Okay, say that as 10. Okay, from this point on, okay, we know initial velocity, then we can take the derivative of equation 10. That's gonna be f dot of t equal to something. I leave this one out for you to do the differentiation. Okay, what I will just show it to you from this one, that you get the value of b, and the final result for the free vibration response gonna be x of t equal to 0.2 e to the minus 3t. Okay, and then this is sine 5t. Okay, the unit is in meter as is given by, I made the mistake here. The one told me that should be meter per second. But anyway, in this case, we have just only one condition here. Okay, so this is going to be valid for time greater than 0. Okay, this is going to be the answer for this one. So differentiation for this one, call that and solve by yourself. Okay, this should be solution for this one. Okay, last week. Okay, continue from last week about energy method. Last week, energy method, there is one point that I would like to point out from you from last time. But maybe this is an example for you. Okay, if we have the system under gravity, or just acting under gravity in vertical orientation, as before we have done this in Newton method. Okay, I just summarize real quick for this one. Okay, we have this position for unstretched position, unstretched of the spring. Okay, and then for this one, I go to in the case of dynamics. Okay, during the motion when it's greater than 0. So we're gonna have the whole thing here equal to y. Okay, but another location I miss it out is that if I have this point or this location, okay, this is gonna be the static equilibrium position. Okay, which means that from this point we're gonna have the static deflection of delta. Okay, and as I showed you before from last lecture or from Newton method, okay, we can use this another coordinate x. Okay, so x respect to equilibrium position as I indicate from this one. Delta is the static deflection. I think you know about that. Okay, and the first thing we have the relation y equal to x plus delta. Okay, this is the relation between these two coordinates with respect to unstretched position y and coordinate with respect to static equilibrium x. Okay, and if I take derivative, just say x dot gonna be x dot, and also second derivative x double dot become y double dot become x double dot. This x dot become y dot become x dot. Okay, let's combine this. Let's say 2, let's say 3. The energy that we need to determine the first one, kinetic energy. Okay, start with this one equal to 1/2 m y. I use the coordinate with respect to unstretched position first. So we get this one for kinetic energy. Next, potential energy V. Okay, we're gonna have V sub k equal to 1/2 k. The same from unstretched position y squared. Okay, that's gonna be 5. Don't forget, under gravity we have a potential energy of the mass equal to mg. Okay, and then y. Okay, equilibrium or reference point is here, and then we go down. Okay, under the reference level, so this has to be negative value. That's gonna be 6. The thing that I would like to point out from this one is that we have the total energy equal to T plus V. But in this case, this is gonna be more than total. I might say this one sub OA. Or indicate the overall energy in the system. You can see that when it is static, okay, the spring has the potential energy due to the static deflection delta. That's gonna be when even it's static. So in this case, if we setting for the overall energy, then we're gonna have T gonna be actually I put this one V sub K plus V sub M OA overall energy for this one. So this gonna be 1/2 my dot square plus 1/2 ky square minus mgy. Or in this case, I can just expand this one y dot square. Okay, this become x dot square. Okay, next 1/2 k y is x plus delta square. Okay, and then minus mg y. Y is the same, x plus delta. Okay, I say this 7. If I say this overall energy is sub OA, that's gonna be energy that if we would like to know how much energy is in the system, okay, that's gonna be equal with the static deflection from this one. Okay, but in this case, I maybe let's say this 7 check my mind, and this gonna be at 8. Okay, and if we use the energy method, okay, we take the derivative with respect to time of the overall energy. I take equation 7. That's gonna be easy for me to do the differentiation. And y dot square plus 1/2 ky square minus mgy. Okay, and the right side is 0. Okay, doing the same derivative as in last week. Then we have my dot derivative of y dot become y double dot. Okay, 2y square. Y square is 2y, 2 and 2 divided, we get ky y dot minus mg. Derivative of y is y dot equal to 0. Okay, so we have y dot cancel, and now we have my double dot plus ky equal to mg. And if you turn to the topic that we learned in Newton method, we get this same thing also. Is that whenever you use the coordinate of y is the coordinate with respect to unstretched position. Okay, the right side instead of showing as free vibration, it shows just like it is force vibration. Okay, that's gonna be confusing for you as I showed you before that. So in this case, once we know these two conditions, relation between y and x. Okay, I can put this one m y double dot become x double dot. Okay, plus ky. Okay, y gonna be x plus delta. Okay, this equal to mg. Now we have mx double dot plus kx equal to mg minus k delta. Okay, this result we have it before. Static deflection k delta cancel or balance with the body force mg, and this become an equation of motion for the free vibration system. Okay, so the point the same is that instead of finding the energy from a space position which includes static deflection, so from this case, from vibration analysis, okay, when we have a system in gravity, okay, then the kinetic energy T, you can just set it by 1/2 mx dot square, potential energy just 1/2 ky square. Notice that energy of the mass mg and k delta cancel, so we has no need to write that down. Okay, once we use this one, I made a mistake in writing here. Okay, this is x, this is x, so the x that we show you, okay, x is the coordinate with respect to equilibrium position. Just call it short. So after that, we will do in the same case, okay, as before that. Or you can say that it doesn't matter with the system, okay, if it is in the horizontal orientation. Okay, in this case, I forget to put coordinate, so the coordinate for this one or the energy for this one, they are the same. Okay, that's gonna be the another example to point it out that in analyze the energy for vibration analysis or motion analysis. In this case, whenever we use the coordinate with respect to equilibrium, no need to put this one with mg. Regarding that, we have the spring that creates static deflection, and if you go into the last example last week, I don't know, it may be this one. Okay, in this case, we can equip or set up the system having this spring, the two spring has no static deflection. So delta for this one gonna be 0. Okay, and then all the motion, okay, mg. And actually you can see that the direction of force, okay, from the spring, both of the two springs are parallel with mg. So in this case, it doesn't cancel with the body force. Okay, because as I tell you, at least the deflection, static deflection is 0 for this one when we setting up for the system from both sides of the two springs. Okay, so in this case, then we have V sub m equal to what? mgh. Okay, this one is below the equilibrium. When going down, okay, this is going to be minus mg h. Okay, because equilibrium is the red one, and then all of the point when it's moved down, okay, it's going to be minus h. Okay, similar to this case. Okay, that's gonna be the example for energy method.